Hello all, this is Nicolas Joly. I will be co-presenting this talk with Saar Amar. We both work at the Microsoft Security Response Center, the MSRC. I'm based in the UK, in Cheltenham, and Saar is in Israel. We are very happy to be talking about CHERI today. So why are we here, and why CHERI? Well, the short answer to this question is that we are haunted by memory safety issues. As you can see on this graph, which represents the number of MSRC cases for memory safety issues that we had over the past 5 years, the trend isn't really going down. Memory safety issues is something that we are going to see in the years to come. Why is that? Because enforcing memory safety, this is a non-trivial problem. There are solutions to this, such as safe languages like Rust or .NET. But the problem with this is that this hardly scales. It's very difficult and obviously very costly to rewrite everything in the safe language. So what else can we do? Well, we can push for more mitigations. But the problem with mitigations is that at the end of the day, they only make the attacker's life a bit harder. Those mitigations, they are rarely a silver bullet. And each year, there are events or competitions, like for example Pontoon, that remind us that we are losing the battle. We make the attacker's life a bit harder, but in the end, it's still possible to exploit memory safety issues. So what else can we consider? Well, there are hardware solutions, something like CHERI, for example, and that's why we're here today. So in the following slides, I will be assuming that you've never heard about CHERI, so I will be giving a very short introduction. And then we'll be talking about some vulnerabilities and attacks that we've tried against CHERI. And finally, we'll be talking about some work in progress, and we'll be giving a few words in conclusion regarding our research. All right, let's go. So what is CHERI? CHERI has been developed by folks from the Cambridge University and SRI International with special safety in mind from the very beginning. It extends traditional ISAs such as ARM, MIPS or RISC-V with new instructions to provide special safety. So in our research, I should mention that we've only looked at the MIPS and ARM implementations. The ARM implementation will be referred as Morello in the next slides. So this new model introduces a new data type called capability. So this is a very central point, and we're going to talk about capability in this entire presentation. So pay attention to this. So capability, you can see this as an extended pointer, a pointer with extra information. And such capability takes exactly 16 bytes in memory, plus 1 bit for a tag. So in total, this is 129 bits. So the tag is very important. This is the bit that protects the capability. A capability cannot be forged. It is unforgeable. So if you try to dereference a capability that has a tag set, you will trigger a fault. If you try to overwrite a capability, you will instantly clear the tag. So this tag is super important. So obviously CHERI is a bit more than that, and if you're curious or if you want to know more, I encourage you to have a look at the CHERI documentation provided by the Cambridge University. It's super interesting. So coming back to those capabilities, what can we find in them? Well, we can find, of course, the virtual address. So this is the pointer that we commonly see every day when we're dealing with C. We can find a few other fields, such as the permissions. So this is the permissions to the object pointed by the address. Is it readable? Is it writable? Is it executable? For example, there is another field called OType. So this represents whether the capability is sealed or not. Sealed means that some capabilities can be made immutable or non-dereferenceable, for example. So you can find this by reading the OType field. And the last field that you can find in the capability is the length. So this length is represented using compressed bounds. And because of the compression for large allocations, just slightly more memory can be sometimes allocated. And in this very specific case, it's still possible to get some out-of-bounds access. But those accesses will never lead to some memory safety issues. That's because just a bit more memory has been allocated for capability. This is just a note, but it's important to have that in mind. The next slide is going to show you what's a capability when you're debugging a program. So on the left side, you can see traditional registers, and on the right side, you can see a bunch of capabilities. So for example, this one is C3, which points to some memory that is read and writable. So where are we using capabilities? Well, the answer to that is pretty much everywhere. When you're programming and when you're allocating some objects, for example, whether those are in the stack or in the heap, you will be dealing with a capability. If you're defining some function pointers, you will be dealing with a capability again. And what about under the hood stuff? Well, you will be dealing also with a capability. So say that you're doing stuff in the stack, for example, then you will be dealing with a capability. Say that you're doing some C++ programming and you're dealing with some C++ objects that have some vtable. Here again, you'll be dealing with some capabilities. So when you're programming, the compiler will handle most of the capabilities that the program will be using. And for under the hood stuff, this will be the responsibility of the loader to create those capabilities. So obviously, this model suggests that the programmer is aware of specific changes. Changes like, for example, casts. Casting a pointer to an integer is something allowed in CHERI. However, the contrary is a bit more difficult. You cannot, for example, cast from int to pointer. This is not possible. What you can do is you can cast from int pointer t to pointer. That's allowed. And something also that we need to have in mind is that memcopy or memmove operations are tag preserving, which means that if you try to copy a bunch of capabilities from one place to another, then the tag bit will be preserved. It's very important to have this concept when you think about exploitation. So this is a short slide to show you what's a capability in the compiler after the program has been compiled. So those 3 lines of C code shows a buffer overflow. So here we have a stack buffer of exactly 10 bytes that has been defined. And you can see that a special instruction here is setting the length of the capability to 16 bytes. And if you try to write out of the bounds of these capabilities, then you'll get a fault, a sick prot. If you are trying to read out of bounds of this capability, you get again a sick prot. So this is almost the same example, but this time with a heap. So here we haven't shown the location where the length of the capability is set, but this is basically the responsibility of the allocator, here in this example of malloc. Malloc will set the length of the capability, and then the program will use it. And here, since we are trying to write out of bounds of capabilities, we'll be triggering a sick prot. So if you followed so far, and if you like to write exploit, now is a good time to start worrying about sharing. Why? Well, CHERI has 2 main impacts. The first impact, obviously, is for spatial safety. Out-of-bound vulnerabilities, those are no longer a security concern. They are deterministically mitigated, which means no buffer overflows, no stack overflows, no things like that. And the other consequence is that one cannot manufacture a pointer. So think about attacks like ROP, where the attacker is trying to craft some arbitrary pointers. Those are no longer possible. So in summary, CHERI is a game changer for the attacker. Trying to exploit a memory safety issues is something that is much harder for the attacker to do. Let's see some quick example. So if you have a primitive where you can corrupt a few bits or perhaps the entirety of a pointer, then CHERI is going to raise a tag bit violation. So this violation won't happen on the moment that you corrupt the pointer. It will happen on the moment you're dereferencing it. If you try to read or write out of bounds of a buffer, you will get this time a length violation. The only corner case where it would still be possible to get some buffer overflow is when you're trying to overflow from some intro objects. So typically some C struct where you'd be using a buffer followed by an integer or a pointer or something like that. In that case, it would require a special compiler flag to get rid of those issues. So what else? Well, there isn't only spatial safety. The problem is that there are other issues, such as temporal safety issues, like double freeze, use after freeze, etc. Those are still theoretically exploitable with CHERI. There are other things also, such as type confusions or uninitialized memory vulnerabilities. And actually, Saar, in the next slides, is going to give you a very interesting example of this. And so now I'm going to leave you with Saar, who will be talking about those vulnerabilities. One last word, CHERI is very good at mitigating exploits. It makes writing exploits a task much harder than what it was before. All right, Saar, it's up to you now.
Thank you so much, Nico, for this great introduction. Now, so let's discuss some of the attacks that are still possible on CHERI supported platforms. So as CHERI ISA does not mitigate type confusions at the architectural level, we can still create type confusion scenarios between different C++ objects. This of course yields the very powerful exploitation primitive of calling arbitrary existing methods of different objects vtables. And from this we can of course corrupt some important metadata, to escalate privileges, and to trigger some information disclosures. All of that actually very reminds me the famous pack bypass that was found in Objective-C and relied on the fact that the ISA pointer was not protected by pack. This is from the amazing talks Salo had at 36C3, and as you can see, before the pack era, we could just corrupt the ISA pointer and fake the entire class descriptor with all of the vtables, function pointers, and basically everything. And this just gave us the primitive of gaining full control over the PC register and jump to an arbitrary address. Now, given pack, this is no longer possible, of course, because all of the function pointers and all of the references to code are signed by pack. That being said, the ISA pointer itself was not signed by pack at the beginning. It is today, by the way, because it was a tagged pointer. And therefore, we could still corrupt the ISA pointer and make it point to a fake class descriptor that contains valid, legitimate vtables. And this, of course, gives us the exploitation primitive of calling arbitrary existing methods in different Objective-C objects. These kind of type confusions attacks are very powerful, and they are still possible on CHERI. Okay, now let's discuss exploitation over CHERI ISA from a high-level point of view. So we all know how this classic circle of life works, right? We find some awesome zero-day, we shape some memory layout, we trigger the vulnerability, we do corruption of some target structure, and from this point we gain arbitrary or relative read-write primitives, and from this point it's a game over, it's a clear win. Now, given CHERI, this phase of gaining relative arbitrary read-write primitive is actually kind of broken in the sense that if you want to gain a truly generic arbitrary read-write, you need to gain a capability with a length that spans the entire virtual address space. And there is no good reason the allocator will generate to you such a capability. Please note that this makes the allocator to be, in a sense, some of the part of the TCB, of the trusted components, because the allocator actually uses dedicated instructions to change and edit and modify existing capabilities. So we really need to make sure that the allocator cannot be compromised and that it checks the integrity of its own metadata before it uses it. Okay, great. So CHERI introduces a new restriction, right? We cannot corrupt pointers and we cannot fake pointers in any way. This, of course, applies to everything. Function pointers, vtables, return addresses, structures, buffers, literally everything. We can even no longer do partial corruption, which is a very elegant and convenient trick. For instance, if you want to deal with ASLR and you don't want to leak the entropy bits, so you can just corrupt the LSB part of a pointer and you can move it backward or forward in memory. Such attacks are not possible on CHERI at all, because even if you flip one bit in a capability, you clear the tag and you will just trigger a CHERI exception when you will try to dereference this capability. Okay, so what we can still do is we can move an existing capability from one place to another. And this, of course, opens a pretty wide range of opportunities for us. For instance, if we want to exploit and use after free bug, CHERI ISA does not mitigate temporal safety at the architectural level as well. So we can just replace a structure A with a structure B in memory, and we can choose our structures such that the V tables or some other pointers will be at the same offsets, and we can treat these pointers differently. These kind of type confusions attacks are very powerful, and they can be converted into a very exploitation primitives. Okay, now let's talk about ASLR. This is really fun. ASLR means nothing on CHERI. And because we cannot corrupt or fake pointers in any way, there is zero value for us to know the layout of the virtual address space, right? We really don't care where the stack, heap, and leaps are located because we cannot even use this information in our exploits to begin with. And this is, of course, by design. When people build the model of CHERI, they try to create a threat model where we can assume that we can give the attackers the entire layout of all of the virtual address space, and it shouldn't help them at all. I really do want to make a very important distinction here between bypassing ASLR and generic information disclosures, because while we really don't care about people leaking capabilities and know the layout of the virtual address space, we really do care, and we don't want attackers to be able to leak secrets or confidential data across different security domains. We even have some models, such as the Chrome Sandbox for Windows, that rely on the fact that you cannot leak secrets. In the Chrome Sandbox for Windows, for example, if you leak the port names from outside the sandbox, you can escape the sandbox by design. So we really do care about that. Okay, now let's go to the exploitation. So we have a port of JSC over pure capability CHERI. This is very convenient. We use that in our first offensive research on CHERI MIPS, and we still use that in our research on Morello, which is CHERI on ARM. JavaScript engines are just a great place to exploit vulnerabilities in, right? We have a scripting language, which is highly convenient for exploitation, and ever since Morello, we have JIT, which is fantastic because JIT compilers have been proven to be a very rich place for bugs and for security issues. So it just looks like the right place to start from. And I want to start with an amazing bar, an uninitialized stack in JSC. Full credit goes to Bruno and then to Luca Todesco, the one and only, who did an amazing job exploiting this vulnerability. And all of this understanding of the root cause is based on their work. So let's see what's going on here. So as we all know, registers is a limited resource, right? And in many cases, we need to free up some registers when we have no ones available. And in order to do so, we need to implement some kind of a context switch. We need to take all of the values that are currently stored in the registers and just store them to some piece of memory, stack, heap, or whatever. And then later on, when we want to continue the execution, we need to restore all of these values from memory into the corresponding registers and then keep going. And in many cases, these values are being written to the stack. Okay, great. Now, the JSC register allocator makes this very interesting assumption that allocations happen unconditionally. And this is interesting because if we have some flow in JSC that has a conditional branch and then does a register allocation, it means that we can skip this register allocation, and therefore we may skip all of these writes into the stack. And this is very problematic because if there will be some flow later on that will try to use a value that is corresponding to a supposedly spilled register from before, we just created here a scenario of using of uninitialized value from the stack. And this gets super interesting because we can use the JIT compiler to compile some JavaScript functions that fetch a pointer, or in our case, a capability on CHERI, a pointer from the stack that points to some JS object of a certain type. And you can use our bug in order to make the stack address to contain an uninitialized value. And therefore, we can shape this stack and upfront to drop there a capability, a valid capability, that points to a different JS object of a different type. And this is how we can convert in a very elegant way this uninitialized use from the stack into a type confusion. Okay, great. So let's see some code. So this function, compile string slice, is the function that contains the bug. And as you can see, we have our conditional branch, and then we have some register allocation. And of course, this register allocation may need to write some data into the stack. But if we will take the conditional branch, we just keep the register allocation, and all of this area on the stack will just remain uninitialized. Okay, great. Now, we said that we can control the uninitialize and shape the stack, right? So let's see how we can do it. This is actually super simple. If you want to write some data to the stack, let's just call a function which allocates its own stack frame, and then have this function to write some data into its own local stack frame. And then when this function returns, all of the data that we just wrote to the stack simply remains there until something else will come and override it. So in our case, we can simply implement two different JavaScript functions, opt1 and opt, that are basically identical, and we just use them with different kind of objects. We just pass them as arguments capabilities that points to two different JS objects. So in this case, for example, let's call opt1 with capability that points to a JS object of type A, and then we will call opt with a capability that points to a JS object of type B. And then because of the bug, opt will fetch from the stack a capability that it believes that points to type B, because we use the JIT compiler and we train this function to be compiled with type B. But opt1 actually wrote something to this uninitialized value on the stack, and this something is a capability that points to type A. And this is how we can create this type confusion. Okay, now let's see the POC. And actually we can do more in this POC. We can convert the type confusion to be out-of-bound read in a very simple way. Great work and great kudos to Luca for this exploit again. So what we have here is just a lot of useless accesses to the stack to make sure that we have the stack frame that we want. And then we need to do a type proof. This is very important. We need to fetch for some field in the object, because this will tell the data flow graph that it can emit some structure checks. And this is super important because we have here a type confusion, and these structure checks may break the exploit, and it could cache us. And then we do the bug trigger. We call slice on a string, which calls compile string slice, the function that contains the bug, and this creates the uninitialize on the stack. And then we call get by offset. But this get by offset will be called on an arbitrarily type read from the stack instead of on a proven type. Okay, so this is super simple. Let's see how we can complete this out-of-bound read. So we just need to define some objects. We'll just create an object with 5 fields, and then another object with 4 fields, and then we need to repeat this second object because we have an out-of-bound read here. So we want two continuous allocations on the heap, and different types on JSC are actually allocated in different areas. And then we'll just try to read field A from obj2. But because of the type confusion, we actually use the offset of A in obj1, which is clearly an out-of-bound for obj2. Okay, great, fantastic. Now let's stop for a minute and talk about this, that it's pretty weird that we stand in here and talking about out-of-bound on CHERI, because we said that CHERI ISA does mitigate spatial safety in the architectural level. So yes, it does true, and CHERI does a wonderful job in deterministically mitigate spatial safety at the architectural level. But if you want to get all of these guarantees from the architecture, you need to use it right. For instance, you absolutely need to make sure that your allocators for stack, heap, and global set the accurate bounds in all of the capabilities they return. And as it turns out, in the prototype that we were working on, the CHERI BSD over Morello, all of the allocators for stack, heap, and global did a fantastic job, but the allocator for the JSL heap did not. And it just sets 16K for bounds for all of the allocations that it's the criterions. And this is why this technique works on Morello just as it works on Ubuntu x64 or like iOS or any other platform. Now, this actually was fixed in dev branch of WebKit over CHERI, so we can actually see the difference. On the left-hand side, you can see the main branch with the bug, and you can see that all of the capabilities have 16K for bounds. And on the right-hand side, you can simply see that all of the capabilities have accurate bounds. Okay, great. And this is the commit. Fantastic job by Brett from the University of Cambridge. Okay, now we have a very stable out-of-bound read, right? So let's see what we can do with it. We already agreed that ASLR is out of the picture. It's absolutely not interesting. And this is a good time to talk about structure IDs. Every type in JSC has a unique structure ID, 32 bits that are stored as the first zero of every object. And attackers supposedly need to know a valid structure ID in order to fake objects in memory, because there are many structure checks that make sure that every time that we are about to operate on some object, we need to make sure that this object is of the type that we are expecting from it to be. And back in the day, it was actually very easy to guess and predict these structure IDs. You could just spray a lot of like different types and objects, and then you could guess that, for instance, structure ID 1000 is of a certain type, and it works fantastic, and everybody did it. And because everybody did it, Apple added a randomization that called structure ID randomization that does exactly what its name suggests. It just randomizes all of the structure IDs. And this is a very good example for mitigation that it would be very interesting for us to bypass on Cherry, because even though there are many mitigations that we might remove given Cherry, such as ASLR, and some others, this is a very good example of a mitigation that we still want to keep around because it makes faking structures more difficult. Okay, so let's try to leak some structure ID. And this is actually something that you can see in many WebKit exploits today. Most of the exploits just open with leaking a valid structure ID. Okay, this is the commit that added the randomization of the structure IDs. So this is the part of like our POC that JIT compile the JavaScript functions, and as you can see, we have here the definitions for all of the objects, and we set a pattern here in obj2 and in victim so we could identify them in memory. And this is on Morello, and you can simply see that obj2 and victim are allocated continuously on the heap, and that the first zero in both of these objects is the 32-bit structure IDs. And clearly, we can understand that if we will just trigger the out-of-bound read from obj2 to victim, we will just fetch and read the structure ID of victim. And this is exactly what happens. And now we will go back to Nico, which will show us the second vulnerability and the second exploit. Thank you.
Thank you, Saar. That was super interesting. So we first had a look at Cherry in summer 2020. And we looked particularly at JSC on Cherry BSD on actually Cherry MIPS. So the question that we had was that we knew that Cherry was really good at mitigating spatial safety issues, but we knew that there was still a concern with temporal safety. So our question was, provided with spatial safety, would we still be able to exploit a temporal safety issue? So to try to solve this question, we looked at JSC, and we wanted to have a look at some CVEs and see if we could still exploit those. The problem that we faced is that well, one of the problem with JSC on MIPS is that the JIT is unsupported, and there was something else like the GC garbage collection that wasn't really working, so we couldn't really trigger some use after free issues. So instead, we went for the easy way, and we introduced a stack use after free, a stack UIF. So why this kind of issue? The reason is a few years ago, we had a bunch of these cases in Chakra, and the scenario here was that in some cases it was possible with the JIT to allocate an object in the stack, and because of the bug in Chakra, it would be possible for an attacker later to use that reference, and so this would give him the ability to read and write stuff in the stack. So this was a super powerful primitive. So we were a bit curious about those issues, and we wanted to see how far Cherry would be able to mitigate those. So to do that, we decided to introduce a bug in the array buffer. So something very simple. So here we just changed a couple of lines, and so instead of dealing with the heap, the array buffer would now be dealing with the stack. So the trigger would be super simple. So we would just allocate a normal array buffer, and then we would slice it, and that would give a view to the stack, to the attacker. So what can we do with that? Well, if you know Saar, you know that once you've got your read and write primitive, well, it's game over. So we want to get to the same state, but here we have Cherry to deal with. So first, where do we want to go? First, we want to see if we can copy capability from one place to another without losing the tag bit. So at first, I thought that this would be easy, we would just have to use some known types in JavaScript that would be using 128 bits. The problem with the GIC, at least on MIPS, is that there is no such objects that exist. At most, float takes 64 bits. And so if you try to copy two floats, then obviously you will lose the tag bit. So this proved to be a bit more difficult than expected. So by looking for memmove or memcopy in the source code, we noticed two methods, typed array set and slice. And it turns out that when the destination and source have the same type, it's possible to enter this particular piece of code. And here, as you can see, there is a memmove. So which means that if we are using set, typed array set with two array buffers that have the same type, then we'll be able to copy a capability from one array buffer located in the stack to another array buffer in the heap. So that's already a good step. Now, can we read from anywhere? Well, not exactly anywhere. You cannot read from 41, 41, 41, for example. This is not possible with CHERI. You have to read from a valid capability. So what can we do? For example, we can read capabilities in the stack, but can we really read from those capabilities? Well, it turns out that with reentrancy applied on the length argument, we could, for example, trigger again the same issue, and this time alter, change the source array capability. So we would be triggering twice the issue. Once to get into the set function, then we would trigger reentrancy, and then we would trigger again the same issue to overwrite the source array. And in that state, we would be able to read from anywhere, I mean from any valid capability. So this is already a good step. Now, can we write anything anywhere? Well, the answer to that is likely. I'm saying likely because I didn't really explore this possibility. It turns out that the bug that we introduced was already quite powerful. We were able to write things in the stack, so we were able to corrupt pointers. No need to be able to write something anywhere. But if you look at set or slice, it's likely that you'd be able to do exactly the same thing. So now that we have that in mind, where are we going? So ideally, we would want to reach a function that would allow the attacker to execute an arbitrary command, something like system, for example. Where can we find system, libc.system? It turns out that there is one place where we can find it. It's the CHERI capability table. And it also turns out that the CHERI capability table is used everywhere by the compiler. You're going to see tons of references to it in the stack. So this makes it super convenient for the attacker. You can just read a pointer to a CHERI capability table and then traverse that pointer up to finding a pointer to system. So this is what we are going to do. We are going to traverse enough capabilities up to reading system, and then we'll find a way to get RC. So how to get RC? So one could, for example, just try to overwrite a return address with a capability to system. But the problem with that is that because of the calling convention, system would use its first argument in a register. And so if you try to overwrite a return address, then you'd also have to make sure that this particular register would be set to your own value. And because of that, it makes things really hard to implement. It might be possible, but definitely harder. So what we did instead is that we targeted a saved C++ object in the stack. So an object with a vtable. And here, it would be super easy actually to fake a vtable. You can, with CHERI, you just see, you can, as I said in the beginning, a vtable is just, again, a capability to some other capabilities. So something that is easy to achieve with an array buffer. So we would just create an array buffer, and then at some offset in this array buffer, copy the capabilities to system. And that would be our vtable. Something really easy in the end. And so in the end, we just needed to overwrite two pointers, two capabilities in the stack. One for this C++ object and 1 for the argument. And then we will just wait for the stack to unwind to execute our payload. And so this is a result. I agree with you that this isn't very impressive, but at least it works. You can see a ping to some website executed just from loaded a script with JSC. And now I'm going to hand over again to Saar, who will be talking about some work in progress and will be concluding. Thank you.
Thank you so much, Nico. This was super interesting. Okay, so now let's talk about how we can present some hardening of CHERI. So as we saw, CHERI ISA gives us non-forgeable references to virtual memory and bounds and permission check at the architectural level, which is amazing. If we just use CHERI-aware compiler and runtime, we could actually achieve deterministic mitigation for all of the special safety variants, and it's fantastic. And this means that we just left with temporal safety, type safety, allocator safety, and probably some other stuff that we need to care about. And we just want to mention here that there are some fantastic and really impressive work in progress projects that try to present software solutions for these bug classes. A very good example is Cornucopia, which is capability revocation. It's an extension for the virtual memory subsystem in CHERI BSD. It simply presents deterministic mitigation for C and C++ heap temporal safety issues, mostly focused on heap use after freeze. We don't have time to talk about all of the details, but there is a great paper that you can check out, and there is actually the code in a dedicated branch of CHERI BSD that implements capability revocation, so please check it out. Another very important example is JIT. JIT is always a very sensitive and very dangerous place. And for instance, we do want to make sure that we can enforce write XOR-X, right? We don't want to have one physical page that is both writable and executable at the same time. So instead of just having two different virtual mappings, that the first one is read-write and the second one is read-execute, we can just have two different capabilities. That the first one is read-write and the other one is read-execute, and it's very elegant. And this is very good example for the fact that CHERI ISA is also provide us very unique set of abilities in hardware that we can take advantage on from software in order to implement a more elegant and stable software solutions. And this is, for instance, a commit from Brett from the University of Cambridge that implements this idea of just like having capabilities that are only writable or executable in the executable allocator. Okay, so some takeaways. CHERI ISA mitigates a very wide range of bug classes at the architectural level. Fantastic. CHERI ISA significantly raises the bar for exploitation in a very elegant, in a very unique way. And it's very important to keep in mind that CHERI offers a lot of abilities in hardware, just like we said, that you can take advantage on from software. And it's very important to keep in mind that it's only the beginning. There is so much to innovate, research, and to develop in this area. So we absolutely hope that all of you will jump by and will try to help to make CHERI better and stronger. And now it's time for shoutouts. This project could not have been done without an amazing force from many different teams and organizations, MSRC, MSR, Cambridge, and many other partners. We cannot mention all of you, but thank you so much. It was super fun to work together and to collaborate on this project. Here are some references that you can follow on CHERI, and thank you.